Somewhere in your kitchen right now, there is a glass. If it falls and shatters on the floor, you know, without even thinking about it, that it will never spontaneously leap back together, not in 1,000 years, not in 1,000,000,000. And yet, if you looked at the fundamental equations that describe every piece of that glass, every atom, every collision, every vibration, none of them would tell you that this is impossible. Run the equations backward, and the shards flying back into a perfect glass is just as valid a solution as the glass breaking in the first place. So why does it never happen? Why does an egg scramble but never unscramble? Why do stars burn out but never spontaneously ignite from ash? Why do you remember yesterday but not tomorrow? Every single one of these questions is really the same question, wearing a different disguise. It's a question that sits quietly underneath every moment of your life, and it turns out to be one of the strangest unsolved mysteries in modern physics. Why does time only move in one direction? It seems like it should be the easiest question in the world. Of course, time moves forward. What else would it do? But the moment physicists actually looked closely at the laws governing the universe, they found something deeply unsettling. Almost none of those laws demand that time move in only one direction. The universe's rulebook is, for the most part, completely reversible. And yet the universe we actually live in is not. Something added the arrow, something pointed time toward the future and never let it point back. And nobody is entirely sure what that something is, why this question refuses to go away. This isn't just a curiosity for physicists to chew on in their spare time. The direction of time touches almost everything we consider meaningful about existence. Memory only works in one direction. Cause always precedes effect. Aging only moves one way. Even our sense of free will, the feeling that we're moving into an open future rather than a fixed past, depends on time having a direction. If physics can't fully explain why time flows the way it does, then in a strange sense, physics hasn't yet explained why anything happens the way it does. Why we grow old instead of young. Why we can build a house but never unbuild it back into a pile of raw materials with a single natural process. Why the universe seems to be a one-way street when its underlying machinery looks on paper like a two-way one. Scientists have been circling this problem for over 150 years, and while they've made enormous progress, the deepest layer of the mystery, why the universe started in the state it did, remains unresolved. This is one of those rare places in science where you can follow the logic all the way down and find at the very bottom an open question that connects thermodynamics, cosmology, and the birth of the universe itself. The man who first noticed time had a direction. To understand how we got here, we have to go back to 19th century Austria, to a physicist named Ludwig Boltzmann. In the 1870s, the world of physics ran almost entirely on Newton's laws, laws that don't care about the direction of time at all. If you filmed two billiard balls colliding and played the footage backward, it would look completely normal. Newton's equations allow both directions equally. But Boltzmann was fascinated by something Newton's laws didn't explain: gases. Specifically, why does a gas released in the corner of a room always spread out to fill the entire room and never spontaneously collect itself back into the corner? Individually, every single molecule bouncing around in that gas obeys perfectly reversible laws, but collectively the gas behaves as if it has a strong preference for one direction of time over the other. Boltzmann's breakthrough was to realize that this apparent contradiction could be resolved with probability. Imagine you scatter 1,000 playing cards across a table. There's only one way for them to end up in perfect numerical order, but there are an almost incomprehensible number of ways for them to end up shuffled and disordered. So if you start with an ordered deck and mix the cards randomly, of course they end up disordered, not because there's a law forcing disorder, but because disordered arrangements vastly outnumber ordered ones. This is the essence of entropy. Entropy is, loosely, a measure of how many different ways the microscopic pieces of a system can be arranged while still looking the same from the outside. A tidy room has very few arrangements of furniture and clutter that still count as tidy. A messy room has an almost infinite number of arrangements that still count as messy. So if things move randomly, they are simply far more likely to become messy than to become tidy. For exactly the same reason, lottery numbers are far more likely to come up as some random, unremarkable sequence than as 1, 2, 3, 4, 5, 6. Boltzmann's second law of thermodynamics states that in a closed system, entropy tends to increase over time. Not because nature has any goal or design in mind, but because high entropy states are simply astronomically more probable than low entropy ones. Given enough time and enough randomness, disorder wins, not through any active force, but through sheer statistical weight. This was revolutionary. It gave physicists their first real answer to why the universe seems to move in one direction, even while its underlying laws are reversible. Eggs scramble instead of unscrambling because there are unfathomably more ways for an egg to be scrambled than unscrambled. Glasses shatter instead of unshattering for exactly the same reason. The universe isn't obeying some cosmic law demanding decay, it's simply wandering randomly into ever more probable configurations, and it turns out that more probable almost always means more disordered. The puzzle Boltzmann left behind. But Boltzmann's elegant explanation immediately created a much deeper puzzle, one that still hasn't been fully resolved. If entropy naturally increases because disordered states are so much more common than ordered ones, then the universe should, statistically speaking, almost always be found in a high-entropy disordered state, a universe in near-total thermal equilibrium. A shapeless soup with no stars, no structure, no complexity is overwhelmingly the most probable state for a universe to be in. And yet, we don't live in that kind of universe. We live in a universe with galaxies, stars, planets, and living beings, all of which are staggeringly ordered, low-entropy structures. Something, at some point, must have started the universe off in an extraordinarily unlikely, low-entropy state, for entropy to have had 13 billion years to steadily climb ever since. This is sometimes called the past hypothesis. The idea that the early universe, particularly the state just after the Big Bang, must have had unbelievably low entropy, essentially setting the starting line from which everything since has been increasing in disorder. Without this special starting condition, there would be no arrow of time at all. Entropy would simply fluctuate randomly up and down, and the universe would look statistically the same running forward or backward. So the real mystery of time's arrow isn't really about the second law itself. It's about why the universe began in such a wildly improbable, highly ordered state in the first place. And this is where the story becomes genuinely strange, because explaining that initial low entropy condition turns out to be one of the biggest open problems in cosmology. Chapter 1. What entropy really measures. Before going further, it's worth pausing to build a clearer mental picture of entropy itself, because the word gets thrown around loosely and it's easy to misunderstand it as simply meaning mess. Think of entropy less like the amount of clutter in your house and more like the size of an address book. Imagine every possible configuration of a system, every possible arrangement of its atoms as a different address in a giant city. A low entropy state, like an unbroken glass, has a very small number of addresses that count as unbroken glass. A high entropy state, like shattered glass fragments scattered across the floor, corresponds to a colossal number of possible addresses. The pieces could be scattered in an almost infinite number of ways and still count as broken. When a system evolves randomly, it's essentially wandering from address to address. Because there are vastly more addresses corresponding to broken than to whole, a randomly wandering system will, overwhelmingly, end up at one of the countless broken addresses rather than the one rare whole one. This is entropy increasing. Not decay, not decline, just statistics playing out on an astronomical scale. This picture also explains why entropy increase feels irreversible in practice, even though it's not technically impossible to reverse. In principle, it's not against the laws of physics for every air molecule in your room to suddenly rush into one corner, leaving you gasping in a vacuum. It's simply so staggeringly improbable, involving odds so much larger than anything we can meaningfully compare it to, that we can safely say it will essentially never happen in the lifetime of the universe. Chapter 2, The Many Faces of Time's Arrow. Physicists actually recognize several different arrows of time, and part of what makes this topic so fascinating is realizing they may not all be the same thing wearing different masks. The thermodynamic arrow is the one we've already discussed, entropy increasing over time, driving irreversible processes like melting ice, mixing gases, and aging bodies. The cosmological arrow of time refers to the expansion of the universe itself. Space has been expanding since the Big Bang, and this expansion defines a direction, from smaller, denser, hotter states toward larger, cooler, more spread out ones. Interestingly, some cosmologists have wondered whether the thermodynamic arrow and the cosmological arrow are linked, or whether they are ultimately independent of one another. If the universe someday stops expanding and begins to contract, would entropy start decreasing too, effectively reversing time? Most physicists now think probably not. Entropy would very likely keep climbing regardless of whether the universe expands or contracts, because gravitational clumping and black hole formation continue to generate enormous entropy either way. But this question remained genuinely open for decades and reveals how tangled these different arrows can become. The psychological arrow of time refers to the deeply personal experience of remembering the past but not the future. Some physicists, including Stephen Hawking, argued that the psychological arrow is actually a byproduct of the thermodynamic arrow. Memory formation, they suggest, is itself a physical process that increases entropy. Every time you form a memory, tiny irreversible changes happen in the structure of your brain, and this irreversibility is precisely what makes memories only accumulate about the past, never the future. In other words, you remember backward in time because your brain, like the shattered glass, only knows how to move toward higher entropy. Then there's the radiative arrow of time, involving the way waves, like ripples on a pond or light from a bulb, spread outward from a source rather than collapsing inward toward it, and the quantum arrow of time, tied to the strange asymmetry of what happens when a quantum system is measured, a topic still deeply debated among physicists. What's remarkable is that although these arrows feel intuitively connected, physicists haven't definitively proven they all stem from a single unified cause. Most current research strongly suggests the thermodynamic arrow, rooted in that special low entropy beginning of the universe, is the foundation from which the others emerge. But this remains an active area of theoretical work, not a fully closed case. Chapter 3, A Universe of Reversible Laws. Here's where the story becomes even more unsettling. If you examine the fundamental laws governing particles, Newton's laws, Maxwell's equations of electromagnetism, even the core equations of quantum mechanics, nearly all of them are time-symmetric. Run them backward and they still describe a valid physical process. There is one extremely rare exception. In certain interactions involving subatomic particles called kaons, physicists have observed a tiny violation of time reversal symmetry, first confirmed experimentally in the 1960s and studied further at institutions like CERN. This is connected to something called CP violation, the combined symmetry of swapping a particle for its antiparticle and reflecting it in a mirror. According to a deep theorem in physics called the CPT theorem, if CP symmetry is violated, time reversal symmetry, T, must be violated too, in order to keep the combined symmetry of charge, parity, and time intact. This is a real experimentally confirmed asymmetry at the level of fundamental particle physics. But and this is crucial, physicists are confident that this microscopic effect is far too small and far too specific to particle decays to explain the sweeping everyday arrow of time we experience, like why eggs don't unscramble. The overwhelming consensus is that the arrow of time we actually live inside of is not primarily rooted in this tiny particle asymmetry, but in the thermodynamic story of entropy and the improbable low entropy origin of the universe. So we're left with an almost paradoxical picture. Nearly every fundamental law of physics is indifferent to the direction of time, and yet the universe we inhabit is deeply, unmistakably one-directional. The arrow of time isn't written into the rulebook of physics in any obvious way. It emerges instead from the specific starting conditions the universe happened to have. Chapter 4. Roger Penrose and the Improbable Beginning. This is where Roger Penrose enters the story with one of his most striking and controversial contributions to cosmology. Penrose has long argued that the deepest question in all of this isn't why entropy increases. Boltzmann answered that. The deepest question is why the universe began in a state of such staggeringly low entropy in the first place. And Penrose has offered a very specific, mathematically precise way of thinking about just how improbable that beginning really was. He focused on gravity. In an expanding universe filled with matter, gravity acts to clump things together, pulling gas into stars, stars into galaxies, and eventually matter into black holes. A universe with matter spread out smoothly and no gravitational clumping is actually a very low entropy state for a gravitating system, even though it might look orderly or uniform. As gravity does its work over billions of years, clumping matter into stars and eventually black holes, entropy climbs dramatically, and Penrose has argued that black holes represent some of the highest entropy objects that can exist in the universe based on the work of Jacob Bekenstein and Stephen Hawking on black hole thermodynamics. Penrose developed what's known as the Weyl curvature hypothesis, proposing that the initial state of the universe must have had an extraordinarily small Weyl curvature, a mathematical measure related to the clumpiness of gravitational fields. In plain terms, he argued that the early universe's gravitational field must have started out in an almost perfectly smooth, unclumped state, and it's specifically this gravitational smoothness that represents the almost inconceivably improbable low-entropy starting point of the cosmos. Penrose has even calculated just how improbable this starting condition was, arriving at numbers so vast they're difficult to meaningfully visualize, figures involving googles raised to further exponents, describing odds so small that calling them unlikely barely captures it. This leads to one of the most profound open questions in cosmology. Why would the universe begin in such an absurdly improbable state? Standard cosmic inflation theory, the idea that the universe underwent an incredibly rapid expansion in a fraction of a second after the Big Bang, helps explain many features of the universe, like its large-scale uniformity and flatness. But Penrose has argued, controversially, that inflation on its own does not adequately explain this specific low-entropy, low-Weyl curvature starting condition. Many cosmologists disagree with him here, believing that inflationary models, properly understood, do account reasonably well for the low entropy of the early universe. This remains a genuinely contested area of theoretical cosmology, not a settled one. Penrose's own proposed answer is even more radical. His theory of conformal cyclic cosmology, or CCC. In this speculative framework, the universe's ultimate fate, an unimaginably distant future of expanding cooling emptiness, sometimes called heat death, becomes mathematically indistinguishable from the smooth, low-entropy conditions of a new Big Bang. Penrose proposes that when the universe becomes so diffuse and evacuated that only massless particles remain, in a certain mathematical sense, it loses track of scale entirely, and this state becomes equivalent to the birth of a new subsequent universe. In this picture, our Big Bang wasn't the absolute beginning of everything, but the continuation of an infinite sequence of cosmic aeons, with the low entropy of each new aeon inherited automatically from the mathematical structure connecting it to the endpoint of the one before. It's important to be clear about where this idea stands scientifically. Conformal cyclic cosmology is a genuinely speculative theory, not an established one. Penrose and collaborators have pointed to possible circular patterns in the cosmic microwave background as potential evidence. But these claims have been strongly disputed by other cosmologists, who argue the patterns are consistent with ordinary statistical noise rather than genuine signals of a previous aeon. CCC remains a minority position within cosmology. A fascinating, mathematically rigorous idea, but very much unconfirmed and actively debated, rather than a mainstream explanation for the arrow of time. Chapter 5. What modern science says today. So where does mainstream physics currently stand on all of this? Most cosmologists today accept that cosmic inflation offers a reasonably compelling explanation for why the early universe was smooth and low entropy on large scales, even if debates continue about the finer details, including the specific concerns Penrose has raised. Research using data from missions like the Planck satellite has given physicists an increasingly precise picture of the cosmic microwave background, the afterglow of the Big Bang, refining our understanding of just how smooth and low entropy that early universe really was. Meanwhile, black hole physics continues to be an active frontier in understanding entropy. The discovery of gravitational waves by LIGO in 2015, resulting from the collision of two black holes, and the first ever image of a black hole's event horizon by the Event Horizon Telescope collaboration in 2019, have given physicists unprecedented tools to study these extreme objects directly, testing predictions about black hole entropy and behavior that trace back to theoretical work in the 1970s. There's also ongoing research into whether quantum mechanics itself contains a hidden arrow of time, connected to the unresolved debates over what actually happens during quantum measurement, a topic still without full consensus even among leading physicists. Some researchers explore whether entanglement and decoherence, the process by which quantum systems lose their delicate quantum behavior through interaction with their environment, might be intimately tied to the emergence of the thermodynamic arrow at a fundamental level. This is active, ongoing research rather than settled science. Chapter 6. What this means for us. Step back from the equations and the entropy diagrams for a moment and consider what this actually means. Every irreversible thing that has ever happened to you, every memory formed, every wound healed, every meal digested, every year aged, is a direct, personal expression of the same principle that governs shattering glass and expanding gas. The relentless statistical drift from the astronomically improbable toward the overwhelmingly probable. Your entire life, understood at the deepest physical level, is a local pocket of decreasing order, riding on the back of a much larger cosmic story that began at the most improbable moment there has ever been. And there's something genuinely humbling in this. The reason you can remember your childhood but not your future. The reason a fallen tree doesn't spontaneously reassemble itself and leap back onto its stump. The reason time seems to carry you forward whether you want it to or not. All of this traces back not to some active force pushing you through time, but to the sheer staggering improbability of the universe's own birth. You are, in a very real sense, living inside the long, slow unwinding of a cosmic coincidence so unlikely that physicists still don't fully agree on how to explain it. It also raises an unsettling question about the nature of time itself. If time's arrow is not a fundamental feature of the universe's laws, but merely a statistical consequence of starting conditions, does that mean the flow of time we feel so vividly, the sense of the present moment sliding irreversibly from past to future, is, at the deepest level, not fundamental either? Some physicists, following Einstein's own view of spacetime as a four-dimensional block, have suggested that the past, present, and future may all be equally real, and that what we experience as time's flow may be more a product of our brain's own entropy-driven memory formation than a fundamental feature woven into the universe's structure. This remains one of the most contested interpretive questions in the philosophy of physics, without a settled answer. The final thought. We began with a broken glass, certain it would never spontaneously mend itself, and by tracing that simple observation all the way down, through Boltzmann's statistics, through Einstein's block universe, through the strange nearly time-symmetric laws of particle physics, through Roger Penrose's mathematics of an almost impossibly smooth and orderly beginning, we arrive somewhere unexpected. We arrive at the edge of the universe's birth itself, at a question cosmologists still cannot fully answer. Why did everything start in a state so improbable that its steady unraveling is still, 13 billion years later, the reason your coffee cools, your memories form, and your body ages one irreversible moment at a time? Perhaps the arrow of time isn't really a property of time at all. Perhaps it's a fingerprint, the lingering trace of whatever extraordinary event set the universe in motion, still being read out, atom by atom, moment by moment, in every corner of the cosmos. And if that's true, then every time you remember something, every time something breaks and stays broken, you're not just experiencing the passage of time, you're experiencing the echo of the universe's very first and most improbable moment.